You were told humanity learned to fly. That is not what happened. What happened is this. We learned to set mass on fire. We learned to direct the explosion downward. And in the brief window before the fire dies, we fall upward fast enough to miss the ground permanently. That is not flight. That is a controlled detonation with a temporary reprieve from gravitational enforcement. The Romantics called it the dawn of the space age. They showed you photographs, contrails against blue sky, a white needle rising on a column of fire, men in visors waving from gantry platforms. They told you humanity was breaking free. Nothing broke free. The rocket does not escape gravity. It negotiates with it. It makes a transaction, mass for velocity, and the terms of that transaction are set not by engineers, not by budgets, not by political will. The terms are set by physics, by a set of relationships between mass, velocity, and energy that have not changed since the formation of this system, that will not change, that cannot be bargained with. You are sitting on a rock. The rock has mass. Mass curves space-time. Curved space-time resists departure. The rocket is not a key to a door. The rocket is a man running repeatedly at a locked wall, burning himself down to ash in the attempt, occasionally getting a finger through before the wall snaps shut again. This is the architecture of your solar system, not a frontier, not an opportunity, a prison, engineered by physics, maintained by mathematics, inescapable by any mechanism currently available to your species. We are going to examine the walls. We are going to measure them precisely, and we are going to be clear about what the measurements mean. In 1903, a Russian schoolteacher named Konstantin Tsiolkovsky wrote down the operating terms of your confinement. He was not trying to imprison anyone. He was trying to understand propulsion. What he produced instead was a formal description of why propulsion as a mechanism for leaving gravitational wells is a systemic dead end. The equation is this: delta V equals VE times the natural logarithm of m0 divided by mf. We will break this down clinically. Delta V, change in velocity. This is what you need to get somewhere. Not distance, not time. Velocity change. We will return to this concept in detail. For now, delta V is the currency. It costs you something to spend it. V sub E. VE is your exhaust velocity, how fast your propellant exits the engine. This is a ceiling determined by chemistry. Kerosene and liquid oxygen give you roughly 3,500 meters per second exhaust velocity. Hydrogen and oxygen give you roughly 4,400. These are not figures you can improve with better management. They are thermodynamic limits. The energy stored in chemical bonds is finite. It was finite yesterday. It is finite now. M0. M0 is your initial mass, everything, structure, payload, engines, crew if applicable, and fuel, all of it. MF is your final mass, what remains after the fuel is consumed. Structure, payload, engines, crew, just the dry mass. The ratio between them, run through a natural logarithm, gives you your delta V. Now observe the trap. To go somewhere farther, you need more delta V. To get more delta V from this equation, you must increase the mass ratio. To increase the mass ratio, you add more fuel. But fuel has mass. Adding fuel to the initial mass increases M0, which means you now need more fuel to accelerate the fuel you just added, which adds more mass, which requires more fuel. This is not an engineering problem. This is not a problem awaiting a clever solution. This is an exponential relationship that compounds against you. Every additional unit of delta V you require demands a multiplicative increase in initial mass, not additive, multiplicative. The Saturn V rocket that placed Apollo 11 on a lunar trajectory weighed 2,970,000 kilograms at launch. The payload delivered to the moon's surface, approximately 15,000 kilograms. The rest was propellant and discarded structure. You burned, separated, and abandoned 99.5% of the vehicle to deliver 0.5% of the original mass to the destination. That is not inefficiency. That is the rocket equation in operation. That is what compliance with the warden's terms looks like. Now ask what it costs to go to Mars. Ask what it costs to reach the outer planets. Ask what it costs to reach the nearest star. The nearest star requires an energy expenditure so vast that accelerating at 1 gravity continuously for the duration of a human lifetime, you still do not arrive. The mass ratio required for a chemically propelled vehicle to approach any meaningful fraction of light speed produces numbers that exceed the mass of observable matter in the solar system. The equation doesn't break down. The equation is working exactly as intended. You are what breaks down. Forget distance. Distance is a psychological comfort. It gives you the illusion of scale, the feeling that proximity implies accessibility. It does not. What matters is delta V, velocity change, the actual cost of transit in the only currency the universe accepts. To reach low Earth orbit from the ground, approximately 9,400 meters per second of delta V. That is your entry fee to the system. You haven't gone anywhere yet. You are 400 kilometers above the surface, moving at 7,800 meters per second. You have purchased yourself the right to be in the problem, not the solution. From low Earth orbit, consider your options. To reach the moon's surface and return, approximately 10,000 meters per second additional delta V. The moon, the nearest body, 384,000 kilometers. That round trip costs you more delta V than it costs to leave the planet in the first place. To reach Mars, a transfer burns and orbital insertion, approximately 5,600 meters per second one way. Mars is between 56 and 401 million kilometers away, depending on orbital alignment. You wait, you calculate your launch window. You have a narrow slot every 26 months where the geometry is acceptable. Miss it, and you wait another 26 months on a planet where the average surface temperature is -60 degrees Celsius and the atmospheric pressure is less than 1% of Earth's. Mars, the flagship destination, the frontier, the great hope of your species. And returning from Mars costs you approximately the same delta V as going, except now your propellants are gone. They must be produced on the surface. From what? With what power source? At what scale? These are engineering questions that have not been answered in 60 years of serious study. Now look further. Jupiter, the gravitational center of mass for most of the outer solar system, a body so dominant that every object in the outer system is in some sense defined by its relationship to Jupiter. To reach Jupiter from Earth, approximately 6,300 meters per second. To slow down and achieve orbital insertion, another 6,000. To actually reach the surface, a surface that does not exist as a discrete layer, merely a gradient from gas to supercritical fluid to metallic hydrogen under pressures that would compress any known material into unrecognizable geometry, you don't reach the surface. Nobody has modeled a mission to the Jovian core that does not end in total system failure before arrival. Saturn, Uranus, Neptune, the delta-V requirements scale, the travel times lengthen, the communication delays grow. New Horizons, the fastest spacecraft humanity has yet launched, required 9.5 years to reach Pluto. It was traveling at approximately 16 kilometers per second, and it did not stop. It could not stop. Stopping would have required delta-V it did not carry. This is the delta-V map, not a map of distance, a map of cost. And the costs are not linear. They are not manageable. They are, at the scale of human biology and human engineering, prohibitive. Distance means nothing. Gravity means everything, and gravity is everywhere. You would think the sun is easy to reach. It is 150 million kilometers away. It is the center of the system. Everything orbits it. Every trajectory is defined by its gravitational dominance. Surely, proximity to the solar gravity well makes it accessible. Examine this assumption. It will not survive. The Parker Solar Probe was launched in August 2018. Its mission? To approach the Sun more closely than any previous spacecraft, to take measurements within the solar corona, to answer fundamental questions about the structure and behavior of our star. The Parker Solar Probe is the fastest human-made object ever recorded, eventually reaching speeds exceeding 690,000 kilometers per hour during its closest perihelion passes. And getting there required one of the most elaborate and expensive orbital mechanics sequences in the history of spaceflight. Why? Because Earth is already moving. Earth orbits the Sun at approximately 29,800 meters per second. That velocity is not a gift, it is a liability. Every object launched from Earth inherits that orbital velocity. Every spacecraft begins its life as a projectile moving sideways relative to the Sun at nearly 30 kilometers every second. To fall toward the Sun, you must shed that velocity. You must execute a large retrograde burn. You must fire your engines backward relative to your direction of travel, scrubbing off that inherited orbital momentum. To reach the perihelion close to the Sun, you must reduce your sideways velocity dramatically. To reach the Sun's surface from Earth orbit requires shedding almost the entire 29,800 meters per second of Earth's orbital velocity. That is a delta-V expenditure comparable to launching from Earth in the first place. It is more expensive in rocket propellant terms than it is to escape the solar system entirely. Read that again. It costs more to reach the Sun than to leave the system. The Parker Solar Probe did not attempt a direct trajectory. It used 7 Venus gravity assists over 7 years to gradually reduce its perihelion distance. 7 passes by Venus, 7 orbital geometry operations spanning nearly a decade, each one designed to bleed off a small fraction of the probe's heliocentric velocity using the gravitational mass of another planet as a brake. 7 years, 7 planetary assists, an enormously sophisticated trajectory design, and the Parker Solar Probe still did not reach the solar surface. It dipped to within approximately 6.2 million kilometers. The Sun's radius is 696,000 kilometers. The probe came within 9 solar radii. That is not proximity. That is a controlled descent to the lobby of a building you cannot enter. Our own star, the object whose gravity holds this entire system in configuration, and we cannot reach it. We can approach it sideways, using other planets as brakes, bleeding off velocity across years of careful geometry, and we get close enough to take readings from the outer atmosphere. The Sun has a thermodynamic deficit built into every approach vector. Getting there is not a matter of pointing a spacecraft sunward and burning. It is a matter of subtracting velocity you were given at birth, and that subtraction costs more than most missions in history have ever spent. This is not an engineering failure. This is orbital mechanics in a system that did not optimize itself for your convenience. April 13, 1970, 55 hours and 54 minutes into the Apollo 13 mission. Crew: James Lovell, Jack Swigert, Fred Hayes. Position: approximately 330,000 kilometers from Earth, en route to the Moon. At 21:07 mission elapsed time, an oxygen tank in the service module failed catastrophically. The explosion vented 2 of the 3 fuel cells that provided electrical power and oxygen to the command module. Mission status transitioned from lunar landing to survival operation in approximately 90 seconds. And here is the critical data point. The crew could not simply turn around. You might believe that a spacecraft in distress with 3 crew members whose oxygen supply has been compromised would execute an abort and return to Earth immediately. You might believe this because the concept of emergency implies the option of reversal. In terrestrial emergencies, you retreat, you call for extraction, you reverse course. In orbital mechanics, there is no reversal. There is only the trajectory. Apollo 13 had already committed to a free return trajectory, a figure-8 path around the Moon and back to Earth that required no additional propulsion under normal conditions. But the explosion forced the crew into the lunar module, a vehicle designed for 2 occupants for 2 days, now tasked with housing 3 occupants for 4 days, while providing life support, navigation, and orbital correction capability. The spacecraft had to continue to the Moon first. It had to fly around the lunar far side. It had to use the Moon's gravity to redirect the trajectory homeward. This was not a choice. This was the only energetically viable path. The propellant remaining in the lunar module's descent engine was sufficient for orbital correction burns. It was not sufficient for a direct abort back to Earth. The geometry of the cislunar trajectory, combined with the available delta-v, made the lunar flyby mandatory. 3 men, compromised life support, dwindling electrical power, dropping cabin temperatures, and the only available action was to continue deeper into the system before the system's geometry would permit return. Mission Control in Houston was not making decisions. Mission Control was solving a constrained optimization problem. The constraints were fixed: orbital mechanics, available propellant, atmospheric entry corridor requirements, vehicle capability envelopes. Every option that violated any of these constraints was not an option. It was a notation in the margin, something that cannot be done. What remains when you subtract every impossible action is a very short list. That list was executed with extraordinary precision by the crew and controllers. The mission survived. But note what saved it: not heroism, not ingenuity in the inspirational sense. Heroism was incidental. What saved it was the correct application of orbital mechanics to an available delta-v budget under time and power constraints. The math was applied correctly. The trajectory held. The entry corridor was threaded. Apollo 13 was not a story of men defeating physics. It was a story of men obeying physics with exceptional accuracy while everything around them failed. The math does not negotiate. The math does not acknowledge the oxygen reserves. The math proceeds on its own terms, and survival consists of aligning yourself with it before it concludes without you. Consider 2 spacecraft. The Galileo probe, launched October 1989, arrived at Jupiter December 1995, operated for nearly 8 years, returned data on Jovian atmospheric composition, the magnetosphere, the Moon's Europa, Ganymede, Callisto, Io. Evidence suggesting a subsurface liquid water ocean beneath Europa's ice shell. Data of extraordinary scientific value. Mission cost: approximately $1.4 billion. On September 21, 2003, Galileo was commanded to enter Jupiter's atmosphere at approximately 50 kilometers per second. It was disintegrated by atmospheric friction and overpressure within minutes of entry. We did not bring it home. The Cassini spacecraft, launched October 1997, arrived at Saturn July 2004, operated for 13 years, mapped the ring system in unprecedented detail, deployed the Huygens lander to Titan's surface, discovered active water ice geysers at Enceladus's south pole, a finding that altered the calculus of extraterrestrial habitability entirely. Mission cost? Approximately $3.26 billion. On September 15, 2017, Cassini was commanded to enter Saturn's atmosphere at approximately 113,000 kilometers per hour. It transmitted data for approximately 91 seconds before the signal terminated. It was destroyed. We did not bring it home. The question surfaces automatically. Why? The official explanation involves planetary protection protocols. Both Jupiter and Saturn host moons considered potentially habitable. Galileo had already suffered a microbiological contamination concern. An uncontrolled crash on Europa, carrying residual Earth-origin biological material, would compromise the scientific integrity of that moon as a study site. Similarly, Cassini could not be allowed to drift uncontrolled after propellant exhaustion, risking impact with Enceladus or Titan. These are legitimate concerns. They are also secondary. The primary reason is delta V. To return either spacecraft from the outer solar system would require a propulsion capability orders of magnitude beyond what either vehicle carried. The delta V cost of a Jupiter to Earth transfer is approximately 9 kilometers of velocity change at the departure burn alone. Cassini, by the end of its mission, had consumed its propellant budget in orbital maintenance and science operation maneuvers. There was nothing left. Galileo's situation was identical. So we spent $1.4 billion building a system capable of surviving 8 years in the Jovian radiation environment. We spent $3.26 billion building a system sophisticated enough to discover geysers on a distant moon that may harbor conditions compatible with microbial life. And in both cases, the delta V required to retrieve these systems exceeded what we could provide. So we did the only thing the delta V budget permitted. We converted them into controlled impact events. We described the impact of Cassini as a grand finale. We released time-lapse animations. We held press briefings. Scientists described the moment with carefully modulated emotion, but stripped the language back to its operational content. We sent a $3.26 billion scientific instrument on a one-way trajectory into a gas giant because we could not afford the kinetic cost of retrieval. The gravity well of the outer solar system accepted delivery. The asset was expended. This is what the gravity trap looks like at billion-dollar scale. You build the best thing you can build. You send it as far as you can send it. You extract data for as long as the power budget holds. And then the delta V ledger closes, and physics determines the method of disposal. Planetary protection is the frame. Orbital quarantine is the mechanism. The gravity well is permanent. The spacecraft is not. Nothing comes back from the outer system because nothing can. Here is what the data indicates. Humanity is not a spacefaring species. The term is aspirational, not descriptive. A spacefaring species would be one capable of meaningful transit between gravitational systems, capable of establishing itself at multiple locations within a stellar system or between stellar systems, such that the loss of any single location does not constitute species termination. By that definition, we are not spacefaring. We are a single-location biological system that has, on 32 occasions between 1969 and 1972, placed a small number of representatives on a nearby rock for brief intervals before retrieving them, and which has maintained a continuous human presence in low Earth orbit since November 2000. 400 kilometers above the surface, inside a gravity well we have not actually departed. We have probes at interstellar distances, but they carry no passengers, they will not return, and they bear no relationship to colonization, expansion, or species propagation. They are messages in bottles thrown from a cell whose walls we have measured exhaustively but cannot breach. The Tsiolkovsky equation is not a challenge waiting for an elegant solution, it is a formal description of thermodynamic reality, and the reality it describes is that chemical propulsion cannot, at any plausible scale of engineering, deliver biological payloads to interstellar destinations within biological timescales, and that even within the solar system, the delta-V costs of meaningful transit are sufficiently high that every mission we have ever flown has been a one-way or near one-way operation, with no capacity for abort, no capacity for retrieval, and no capacity for error outside the extremely narrow margins built into each specific trajectory. The Sun cannot be approached without shedding the orbital inheritance of our birth planet at ruinous propellant cost. The outer planets cannot be departed from once reached. The nearest star is not a destination, it is a coordinate that might as well be fictional for all the access our physics permits. We are biological organisms with lifespans measured in decades, bound to a gravity well by mathematics that does not concern itself with our preferences, our ambitions, or our survival. Every mission we celebrate is a demonstration not of our freedom, but of the precision with which we have learned to navigate our confinement. Apollo was not a triumph over physics, it was a brief, expensive, temporary, and irrecoverable excursion to a nearby gravitational body that we have not repeated in over 50 years. Cassini and Galileo are not pioneers, they are artifacts that the gravity trap accepted and did not return. The rocket equation does not have a workaround. The delta-V map does not have a discount tier. The solar system is not a frontier. It is a series of nested gravitational wells, each one a trap, each one a one-way street at the scale of what we can build and what we can afford and what biology can survive. And at the outermost boundary of this system, where the solar wind gives way to the interstellar medium, there is no wall, no barrier, no dramatic threshold, just a gradient, a slow thinning, and beyond it an emptiness so vast and so indifferent that the concept of transit loses meaning entirely. We are here, we were born here. The mathematics strongly suggests we will remain here, and that the only question with genuine empirical content is not whether we will escape, but how precisely we will document our failure to do so before the option is no longer under consideration.